The very first book that I read about cathodic protection was the 1953 edition of Peabody's, published by Nace. It had diagrams of equivalent circuits that did not relate to the results of the measurements that I made in the field. So I made one of these circuits out of electrical components and continued to make actual circuits that reflect the real readings of cathodic protection measurements. When we're in the field, we can only see the ground we are doing a survey over, and we see test posts set in remote earth. These are shown on this side of the model. These are the test posts, and the meter is attached between the ground and the test post. When we place an electrode on the ground over a well-coated pipeline, the charges pass through shells of resistance as they pass onto the pipeline metal at a coating fault. This is represented by the structure of resistances that enable voltage measurements to be made between remote earth and the pipelines as experienced when excavating a pipeline and making measurements at the various levels as the excavation progresses. I can show this, and this is the reading that we get when we place the half cell in remote earth. It is the same reading wherever we place it in remote earth. But as we get to an excavation, as the excavation progresses and we dig deeper and deeper, the readings on the meter get less and less. And this is due to the resistance between the pipeline, which we are connected to, and remote earth on which we place the half cell. It is clear from this model that this represents exactly how we find it in the field. Here is the overline pipe to soil potential, and as we go closer and closer to the coating fault, then we find that the resistance between remote earth and the coating fault decreases until we touch the pipeline itself, in which case we're making a measurement straight from the pipeline in one place to another place, and there's no resistance in that part of the circuit.